This slide over here summarizes what we discussed about the jump and link, right? So we talked about the program counter, which is a pointer to where you are in the program. When you execute a jump and link, the program count is updated to be the new procedure address, and the value of the current PC, in fact PC plus 4, is placed in the special register RA. And so this allows you to return back there. So when you're returning control, all you have to do is jump to the address specified in the following register, and that's how you return control back. Now note that when you execute a jump and link, $RA is set to be PC plus 4. That means whatever value was sitting in $RA is being overwritten. Okay, so you've already seen an example of nested procedure calls. So procedure A is now going to call procedure B, right? So jump and link to procedure B, let's say. And then in procedure B, you execute a bunch of stuff. Then you do jump and link to procedure C, right? So when you do this jump and link over here, you're essentially overwriting the contents of RA, which actually keeps track of where B should be returning back to, right? So before you execute a jump and link, if you think your return address has something valuable, you need to save it somewhere and then bring it back again, right? So what I would do in this case is, before executing this jump and link over here, I'm going to do a store which stores the contents of RA into some location in memory. Okay, and then after I'm done with this jump and link, then I'm going to load that value back from that memory location back into $RA. Okay, so this kind of gives you some idea of what else goes in the stack, right? So we said that the stack starts at the top and grows downward, and every procedure is creating its activation record over here. That activation record contains the local variables of that procedure, right? So if procedure C had created variables, let's say integer y goes over here. In addition to that, a few things have to be saved away. In this example, the value of RA may have to be stored onto the stack as well, right? So the stack essentially keeps track of values that need to be saved across procedure calls. So you put something into the stack, and then when you return back from a procedure, you restore values back from the stack into the registers that they should be placed into. And that's the point I'm kind of driving home over here, right? So essentially, the register is a scratchpad. Procedure A might have been written by some programmer. Procedure B may have been written by a different programmer. And so every programmer thinks that when you invoke my procedure, here's a register file scratchpad that I have full access to. Okay, and so when you call a procedure, you should assume that you're essentially losing the register file, right? You're losing whatever is in $RA, whatever is in S0, S1, T0, and so on. And so if you care about any of those values, you need to place them on the stack, then hand control to procedure B, and then procedure B says, all right, here's the entire scratchpad, the entire register scratchpad that I have full access to, and then I can use any values I want. So the stack is a place where you keep not only your local variables, but also parts of the register file that you care about. And we'll get to more details of these as we walk through some examples. Now let's walk through the different steps when you're executing a procedure call or a return. Okay, so let's say that the stack is sitting until this point over here. This belongs to procedure A. Okay, so now before I invoke a new procedure B, A has to save any values that it cares about, right? Because before it hands control to procedure B, it needs to make sure that any values that it cares about which are sitting in register RA or that are sitting in its own argument registers or in its valuable registers S0 through S7, all of those have to be kind of saved away onto the stack. So let's just assume that all of these 8 values, these 4 values, and this 1 value are something that procedure A cares about. Okay, so in this case, it has to save away 13 registers into memory. So it essentially grows its stack. It says, I'm going to increment my stack space until here, and I'm going to create room for 13 more values. Okay, and having done that, it says, all right, now I'm ready to hand control over to procedure B. Now note that while this was happening, even the value of the stack pointer got updated. So $SP, which used to point here, has now been updated to point to the new end of A's activation record. Now you place arguments for procedure B into registers A0 to A3. Then you execute the jump and link. Okay, and now procedure B is going to be executing. Now procedure B says, well, at the start, I'm going to create some space for my local variables. Okay, and so it grows the space. It updates stack pointer to now point over here. And procedure B is now going to place its local variables over here, right? So X, Y, Z, all of that gets placed on the activation record for procedure B. Once procedure B is done, it's going to place the return value into register V0. It's going to free up the stack space, and that's as simple as changing the stack pointer to point back to its original location. Okay, and I'm calling SP an increment because note that you start at a high address and you're going down to lower addresses, right? So pushing things onto the stack is like decrementing the stack pointer, and popping things out of the stack is like incrementing the stack pointer. Now, when procedure A has control back, it's going to do a few things. It has to bring all of these 13 registers back, or these 13 values back into its respective registers. So those get copied back into $RA, A0 to A3, S0 through S7. And once that is done, A is going to readjust its stack pointer to point over here. Okay, and once all of this is done, A is now going to resume whatever it had to do after the procedure call. Okay, so these are the many steps involved on both a procedure call and on a procedure return. And again, these will be made much more clear as we walk through a few examples. So let's walk through this very first example. This is on page 98 of the textbook. And this procedure is called a leaf example. So a leaf procedure is a procedure that does not itself call other procedures. So it's kind of at the leaf of a tree. Okay, so this procedure is very simple. It gets 4 arguments, GHIJ. It does this computation, and then it returns the value of that computation, which is called F. If you look at the assembly code corresponding to this procedure, this is what it looks like. It starts at label, leaf example. Let's ignore these 4 instructions for starters. Once those 4 instructions are done, I'm now going to get into the body of the procedure, which is to do that math, right? So it first takes G and H and adds them. G and H are provided as the first 2 arguments, so those values should be sitting in A0 and A1. So I add A0, A1, place the result in a temporary register T0. Then I add the next 2 arguments, A2 and A3, place the result in a temporary register T1. And then I subtract the 2, so T0 minus T1. Result is what corresponds to F. I've decided to create a register S0 for F, right? Since this corresponds to an actual variable, I'm going to use an S register for this instruction. Okay, and now having done that, I'm going to place that result back into V0 because my return value should be in V0. So I do that by moving the value in S0 into V0. Since MIPS does not provide a move instruction, the only way I can move that value is by just adding S0 to 0 and then putting the result into V0. Now having done that, I do these 4 more instructions, which I'll get to in a minute. And then I end by just doing jump to whatever address is placed in register RA, right? And this way I hand control back to my caller. Now let's talk about these 4 instructions at the top and these 4 instructions at the bottom. Okay, now the body of this procedure is using registers T0, T1, and S0. Okay, now this procedure is being extra nice. It makes the assumption that these registers are somehow important to the caller, and so when this procedure is done, it wants to make sure that it leaves the processor in the same state that it found the processor, right? So there might have been something valuable sitting in T0, T1, and S0, and so in order to be nice to the caller, this procedure says that I'm going to save whatever values are in T1, T0, and S0 onto the stack, and then when I'm done, I'm going to copy those values back into those registers and then leave things just the way I found them. Okay, so that's why you start by storing the contents of T1, T0, and S0 onto locations on the stack, right? So you're essentially growing your stack by 12 bytes to accommodate these 3 4-byte values, right? So you start by decrementing the stack by 12, which means you're growing the stack by 3 entities, and then you're doing these stores and placing values onto the stack. And then when you return, you're essentially loading from those same locations and putting them back into registers, and then incrementing the stack, that is returning the stack back to where it was originally. So this is an extra nice procedure call, which is very careful about handling all these registers. So you'll see that in this very simple procedure, which is made up of basically these 3-4 instructions, you had to add a whole bunch of overhead instructions to save stuff onto the stack and then restore values back from the stack. Okay, and that overhead can be pretty high. So to make things simple, we are going to assume that the contents of registers T0 through T9 are not very important, right? So the caller should be careful to not place anything important in those registers. And in fact, the caller should assume that when you call a procedure, that new procedure is likely to overwrite whatever you had in those temporary registers. And so you can expect garbage when that procedure comes back and returns control back to you. Okay, so if you make that assumption, then the callee procedure need not bother storing the values of T1 and T0 onto the stack, right? So that helps remove these two instructions and these two instructions down over here. Okay, it's only variables such as S0, S1, and so on that have to be carefully saved away onto the stack and then restored after the procedure call. In this particular example, I really didn't have to use register S0, right? What I could have done is subtracted these two values and put them straight away into register V0. Had I done that, I could have avoided using S0, which meant I could have avoided storing this onto the stack. And that would have made the procedure much more efficient, right? That's why I've said over here that by writing a carefully optimized program, I could have avoided using the stack altogether. So use temporaries when you can, because the assumption is that temporaries are fair game and I don't have to save them onto stack and then restore them across procedure calls. Okay, and in this case, I can even optimize away the use of register S0.